Hello guys, I'm Alexander Renchog, and as Anne already introduced me, you know that I will be accompanying you through the exercise sessions associated with applied supply chain analytics. And I've prepared a little bit of something for you today. On the one hand, we'll talk a little bit about how the practice material is organized. Then we'll dive in and talk a little bit about programming in terms of its computational model, different abstraction levels, and we'll see how Python differs from other programming languages when talking about compiled versus interpreted languages. And then we'll motivate Python, our choice in it. We'll discuss available IDEs, the one that we are using, and then I will show you in a short demo how to open up your IDE and start working technically. All right, so as you all know, we have three parts to ASCA. On the one hand, we have lectures that are guided by Anne. Then we have the exercises and the challenges where you guys can show off your skills. In terms of exercises, we have three components to this. On the one hand, the slides, such as these that I'm presenting now. And then you'll have Jupyter Notebook tutorials where most of the content in the slides will appear again in the form of code, and you will get to rehearse everything that you're learning, and you can try things out directly there. And when you feel ready, you can go over to the practice problems and test yourself. And these Jupyter notebooks look somewhat like this. You will be able to do everything from the comfort of your browser. You'll have Markdown with text and images and everything documenting these tutorials. And you'll have links within an overview notebook that will send you directly to that particular segment of the exercise, right? These are the tutorials here and there, and you'll have the exercise sections immediately underneath, right? Now, let's talk a little bit about programming. So, what is a program? It's actually a pretty basic definition. It's a list of instructions to be executed on the machine. It's analogous to a recipe of sorts. And as with the recipe, the instructions in and of themselves aren't enough. You need other things. You need data, as in ingredients, and diverse dish stages, as in intermediary results, until you get to your final dish, which is the output. And as with the dish, you need some pots and pans to store the diverse dish stages and your ingredients and all, and this is done by means of memory for the program situation. And then you have your stove, the CPU, which executes the program. It's split into two. On the one hand, the control unit, and on the other hand, the arithmetic logic unit. The control unit just tracks where you are at with your recipe, and the ALU executes them, basically cooks everything. And these things fit together in what is called a von Neumann architecture. Here you have, this is the model of computers today. You have input-output modules with which you communicate, by means of which you communicate with the computer, with the processor to be more precise, right, by means of a memory. And the processor in and of itself is actually pretty stupid. Like the control unit just loads stuff for the arithmetic logic unit to execute, and the arithmetic logic unit can only execute simple operations, addition mainly and multiplication. All right, why am I telling you all of this? Because you need to know how you get from code that you can understand to what the machine understands, which is just this, just binary language. It can only add binary numbers, right? But it can do everything, because if you do the right sequence of this, you will get anything you need. We just need several levels of abstractions to be able to write something concisely and have it executed on the machine. And for this, you use meta programs of sorts, like compilers or interpreters or virtual machines, to get from this level where you understand the simple program of adding two numbers to something that is completely abstract for us. All right. And there are a few ways of dealing with this translation from high-level language, from your source code, to the machine language here. On the one hand, you have compiled languages such as C or C++. In this situation, the compiler, this meta program, takes your entire source code, the thing that you understand, and translates it for this particular machine into machine-readable code. Takes a while, and then you're done, and then you execute this, and then you go line for line through your translated machine code and provide output as needed. Then you have hybrid languages such as C#, Java, or Python. Python in one of the modes at least. Here you take the source code, the input. This gets translated by a compiler into an intermediary level, also called object code in Python and bytecode in Java. And this code is run on a virtual machine, which again translates from this intermediary level in the actual machine level and the actual machine language, and then presents you with the output. Last but not least, you have interpreted languages where this metaprogram called the interpreter takes instruction for instruction from your source code and translates that particular one into a machine understandable one, executes it, and then goes on to the next. Right? There are advantages to all of these. Interpreted languages and these intermediary things are portable. Once you wrote the code, you don't need to compile it, to translate everything for different machines. You can just run it here and here, whereas for compiled languages, you cannot do that. Compiled languages, on the other hand, are fast. Once you're done translating everything, you have machine code which can be run directly. Right? Basically, it takes less to get from high-level code to machine code, more that than from this intermediate level to machine code. Okay, having said all that, let's now see why we chose Python amongst everything else.